Okay, welcome to Anna's video on the difference between calculating delta H with H's and calculating delta H using bond enthalpies, and why it is that they're the opposite way round. So we're going to start with calculating delta H with enthalpies, with H's, and then afterwards we'll look at doing it with bond enthalpies, which is different, and we'll see the differences between them. So before we actually get onto enthalpies, I want to show you two other examples which help explain why enthalpies works the way round it does. So if, for example, we have a thermometer and the temperature started at 15 degrees and ended at 20 degrees, and we was trying to find the delta T, we would do the end temperature minus the start, right? If you start at 15 and you end at 20, then your delta T is plus 5, not minus 5. So when you're taking the start and the end, and you're finding the difference, the delta, it's end minus start. So 20 minus 15 plus 5. Same for a volume or a tetra, if you're doing a titration. The delta V or the tetra would be the end volume minus the start. In this case, 12 minus 0, which would be 12. Yeah, the difference here would not be start minus end, otherwise your difference in volume would be minus 12, which isn't correct. So it works exactly the same way with delta H's. If you want to find the difference between your start and your end H, we would do the final, the end H. Well, what do you end up with? You end up with the products, don't you? These things here. I'll just use an example. H2 plus I2 goes to 2HI. So that would be the H of my products, essentially the end H, enthalpy, minus the start H, which of course is the H of the reactants. So if you're using proper full enthalpies, H's, you would do the H of your products minus the H of your reactants there. Comparatively, what we can also do is use bond enthalpies. Now, bond enthalpies kind of work the opposite way round. So let's have a look at bond enthalpies now. So here's my reactants, H2 and I2, and we want to get from my reactants to my products. So let's just follow that pathway. So the first thing we need to do, you have to start with your reactants, because in a reaction, you start with the reactants. So that's where we need to start. And what do we need to do to those reactants? We need to break their bonds. So that's the first thing. That would be the activation energy. We need to break the bonds. And that gets us up here. And I guess you can think of that as just some separate H's and I's if you want. Well, bendomexo. If we're breaking the bonds of the reactants, that's endothermic, and endothermic is positive, isn't it? It has a positive delta H. So the first thing we need to do to get from here to here is we need to break the bonds in our reactants, and that is endothermic, so that must be positive. So that is plus the bond enthalpies of your reactants. We then need to get from here to our products. Well, what do we need to do to get from the top to the product? We need to make the bonds in the products. Again, good friend bendomexo, making bonds is exothermic, and think about the sign for an exothermic reaction. It's negative, so we're going to then subtract the bond enthalpies of our products. So annoyingly, it is the opposite way round between the two methods. If you're using full enthalpies, full H's, it's products minus reactants. If you're using bond enthalpies, you can kind of get rid of this plus, can't you? But it's plus the reactants minus the products, kind of the opposite way round. If you forget about the bond enthalpies one, you can figure it out just by quickly in your head or on the page sketching out a little enthalpy of profile diagram. Doesn't matter whether it's for an exo or endothermic, it'll still be the same. You're going to need to break the bonds in your reactants, bendo, positive, make the bonds in your products, exo, negative. And so these are the two results to remember.